soil and the soil heterogeneity would magnify this horizontal component of the flow velocity, regardless of the irrigation pattern. However, the high computational cost of the current implementations of the ensemble-based computations, such as the ensemble common filter that I just mentioned, limit their use in two-dimensional and the three-dimensional setting. And so how do we address these challenges and solve these issues and to come up to develop an efficient estimation strategy to estimate the evapotranspiration rate? And that's how my work aligns with these motivations. We aim to design computationally efficient data assimilation methods to infer the evapotranspiration rate from the soil moisture data in high-dimensional settings, such as two-dimensional or three-dimensional, relevant to smart agriculture in a setting representative of drip irrigation, and we consider a soil heterogeneity and the spatial variability of the root density distribution. And such efficient strategies would serve as design tools for smart agriculture, for example, to optimize the irrigation schedule and the placement of drippers and sensors. So I simulated the water infiltration in a two-dimensional soil domain. We consider rows of plants, and here are these black ones arrows. They are the dripping devices, and I consider 5 plants in the domain. And the volumetric water content, theta, and the pressure head, phi in this domain can be predicted by this Richards equation, two-dimensional Richards equation. And the K is the unsaturated hydraulic conductivity. We consider the soil anisotropy and the heterogeneity, so it is a second-rank tensor. T is the sink term in the Richards equation, represents the plant transpiration or root water uptake function. And we impose a free drainage condition at the lower boundary, and that there are no flux conditions on the left and the right boundary. At the upper surface, the water flux equals to the water flux from the drippers into the soil domain, and minus the evaporation from the soil surface. And the ND here is the number of drippers we use in the system. And the XDK is the location of the drippers, and the PT is the flow rate of each dripping device. And the evapotranspiration rate in the that we want to estimate, it consists of the transpiration rate and the evaporation rate. They are given by these two canonical forms, and F root here is the root density function, and the gamma T and the gamma E are the root uptake water stress response function and the evaporation reduce factor. And the Tmax and Emax are the maximum the potential transpiration rate and the maximum evaporation rate. And these Tmax and Emax are the only uncertain or random coefficients in this system. And here are the plots that shows the distribution of the isotropic saturated hydraulic conductivity. We use a log normal distribution, and this is the normalized root density distribution. And our goal is to estimate the evapotranspiration rate from the soil moisture sensor measurements. And so in order to do this, we place several sensors in this two-dimensional soil domain, denoted by these red stars. And the difference between the observation soil moisture, theta KL, L denotes the location, and K is the time step, is the difference between the observation soil moisture and the true value of the soil moisture is due to a random measurement error. And we model this random error has zero mean Gaussian white noise, and the data vector is characterized by this multivariate Gaussian PDF. And with this soil moisture sensor data, there are currently two methods that are widely used to estimate the evapotranspiration rate. The first method estimates the evapotranspiration without solving the Richter's equation. The soil domain is discretized into the observational mesh consisting of n sensor elements, and the total ET rate is related to the prescribed flow rate of the dripper and to the observed soil moisture by the water balance approach. This method is very fast to implement because it does not solve the Richter's equation, and but it has low accuracy because the quality of this estimation depends on the quality and the quantity of the available data. And it provides no spatial variability of the evapotranspiration. We can only get the total evapotranspiration rate in the domain. And the second method that is widely used is a data assimilation approach. And the soil moisture content predicted by solving the Richter's equation is updated with the soil moisture measurements. And the total evapotranspiration rate is calculated from the also from the water balancer approach, but we use the updated soil moisture from the data assimilation approach. And this approach is more accurate, but it is very computationally expensive in a high dimensional, like 2-dimensional or 3-dimensional setting, because it solves the expensive Richter's equation in this 2-dimensional and the 3-dimensional soil domain. And still, it does not account for the spatial, we cannot resolve the spatial variability of the evapotranspiration rate. So how do we address these challenges and to overcome these difficulties to get efficient methodologies to estimate evapotranspiration rate based on the soil moisture measurements? So we have proposed an efficient implementation of the ensemble common filter. And in our novel implementation, instead of treating the soil moisture as the updatable observable in a traditional ensemble common filter approach, our approach treats the sink term, the evapotranspiration sink term, as an updatable observable, and which is given as the difference between the soil moisture when solving the Richter's equation with the sink term and without the sink term. And then we replace this random model prediction theta with the measurements data, the soil moisture measurements, and we make use of the observation matrix, and we could approximate the sink term with this YK term. And this YK has the same PDF as the soil moisture data, and these are the mean and the covariance of this PDF. So in this procedure, rather than assimilating the soil moisture data D, we assimilate this rescaled YK. And we treat the Tmax, the potential transpiration rate, and the maximum evaporation rate as independent Gaussian variables. And so we could get samples. We draw several samples of these values of Tmax and Emax, and then we assume the prior PDF of the sink term at observation time Tk to be multivariate Gaussian. This can be like from the values of the Tmax and the Emax we draw from the ensemble, and then we the prior PDF can be updated on the observed value of the random data y by means of this Bayes rule. The posterior is proportional to the likelihood and the prior. And the likelihood function is constructed by treating as a function of the sync term S and the PDF of the data K conditioned on the model predicting the value of the state variable. And then we can get the posterior based on the common update. And they are we can get the mean and the covariance of the sync term. And in this implementation of ensemble common filter, we need the initial guess of the Emax and the Tmax. We need the prior information of these two parameters. But what should we do in the case when prior knowledge of Tmax and Emax are not sufficient? So we propose another efficient strategy to estimate evapotranspiration rate without the prior information of Tmax and Emax. And this method is based on the maximum likelihood estimation. So first, we wrote down the loss function is a measure of mismatch between the observed soil moisture and the predicted soil moisture. And we can rewrite the loss function based on the transformation that I just showed in my previous slides. And this loss function is related to the measurement and the water content by solving the Richards equation when setting the sync term to 0. And we solve this minimization problem by gradient descent, and the components of the gradient can be computed analytically. And these are the gradients, and then we update the Tmax and Emax, and we solve this minimization problem. And this implementation of maximum likelihood estimator is accompanied by the Fisher information matrix to quantify the uncertainty. And let's see some results by using these two estimators. We conduct a synthetic study. We simulate the flow in a two-dimensional soil domain, like 10 meters in width and 1.5 meters in depth. And we place five drippers by the plants, and they are the dripping irrigation occurs at like 24 hours, 74 hours, and 124 hours, and 174 hours. And each irrigation lasts for 4 hours. And we solve the Richards equation and get the soil moisture and the evapotranspiration in this domain. And they are shown by these animations. And then we generate the soil moisture data from the synthetic soil moisture, and then run our novel implementation of ensemble common filter and maximum likelihood estimator to get the estimation of evapotranspiration and the soil moisture. And here show the predictions by using the ensemble common filter that we developed there, and comparing them with the ground truth, the synthetic soil moisture and the synthetic evapotranspiration rate. I'm only showing the results of using the ensemble common filter here. MLE shows a similar result, so I'm not showing that animation here. And for we can quantify the errors in these estimators by computing the error, the relative error, mean square root error. They are for the sync term and for the soil moisture, and we could see that the root mean square error for the sync term predicted by the ensemble common filter and MLE, they are very close, and MLE performs a little bit better in predicting the soil moisture. And we also show the predictions of the total evapotranspiration rate in the domain to add up the evapotranspiration in the soil domain, resulting in the total evapotranspiration rate. And there are 3 plots here. This plot shows the prior statistics of the ensemble common filter, and these green dots denote the true values of total evapotranspiration rate generated from our synthetic study. And these are we use a prescribed time series of Tmax and Emax to generate this total evapotranspiration rate. And by using the ensemble common filter, we developed the maximum likelihood estimator. And here are the posterior plots for the total evapotranspiration rate. And the prediction accuracy is quantified by the evaluation matrices such as the relative bias, the correlation coefficient, and the relative measure. And we can see here, we have a small error bound when using the ensemble common filter, and the relative bias is quite small. And this, by using ensemble common filter and MLE, they have very comparable evaluation matrices. And the ensemble common filter perform a little better than the MLE, even though the bias is a little higher, but it has a correlation coefficient and relative measure that are closer to 1 than using the MLE. So our 2 methods of using ensemble common filter and MLE, they provide a pretty accurate estimation of the total evapotranspiration rate. And next, we investigate the computational efficiency of our ensemble common filter and MLE algorithm. And we compare them when using the standard ensemble common filter that updates the soil moisture instead of updating the sink term in our ensemble common filter. And we can see that the computational that by using our novel ensemble common filter that updates the sink term, the computational time is around 2 orders of magnitude faster than using the traditional ensemble common filter. And by using our MLE, the computational time is 1 order of magnitude faster than using compared with the traditional implementation of ensemble common filter, even for an ensemble size of 200 members. And this effect is magnified when we increase the size of the ensemble. And the left figure shows the number of irritations when performing the maximum likelihood estimator. So the average number of iterations, like with respect to time, is around 13 iterations per time step. So, and it is pretty fast. We use adaptive learning rate in this procedure to accelerate the convergence. And for conclusion, we developed 2 efficient strategies for estimating evapotranspiration rate from the soil moisture sensors in the presence of considerable horizontal flow component due to heterogeneous soil properties and the drip irrigation pattern and the non-uniform root density distribution. And these algorithms are significantly more efficient than the traditional implementation of ensemble common filter that updates the soil moisture in their implementation. And these 2 strategies could facilitate their development as design tools for a smart agriculture for the optimization of irrigation schedule and the dripper placement and the sensor placement. And I want to acknowledge my advisor, Professor Daniel Tadakowski at Stanford University, and these are two related publications that I just talked about today. And thank you very much for coming to my talk, and I'm happy to take any questions.
Thank you so much for such a wonderful presentation, Ryu. If there are any questions for Dr. Lee, please feel free to write them in the question answer chat box. Otherwise, you can just send them to me as well. So while we are waiting for people to type, I'll start with my own question.
Yeah.
So I was just wondering, particularly when you showed the last slide, that you've done this very nice synthetic experiment. So what are some of the limitations that you foresee if you were doing this in an actual field where actual drip irrigation was happening, and then calculating the evapotranspiration soil moisture?
You see, so when what limitations like I could forecast when applying my algorithms in a field study?
Yes.
Yeah, so that's a great question. Like as I haven't done any field study yet, I carry out the synthetic study because I want to evaluate how my algorithms perform. And I think in the field study, I think the limitation is about the computational cost, considering how large the computational domain would be, because now I'm studying a very, very small domain, like this about the size of my garden where I plant some orchids, for example. But when applying for in a real field, I think I need to adjust the like the size of each of my machine and how to perform a field study, and to run this Richards equation in a two-dimensional. I think in field study we're talking about a three-dimensional setting, and that would be expensive to solve. So the computational time is higher. Even though my new approaches provide like estimates of evapotranspiration rate to orders of magnitude faster than the existing approach, but it is still a challenge. So the next step in my future work, I'm considering of implementing my new approaches with like assumption of treating the soil domain as 1D pipes to accelerate this procedure to get even faster prediction.
Right. So when you say 1D pipe, so we're talking just about the flow of water vertically or just horizontally?
So we approximate the two-dimensional or three-dimensional domain as connected pipes to simplify the treatment. I think there is a name for such treatment that we describe in the paper. And I think another thing to carry out a field study is that about the soil property in the field, that should be information provided in this algorithm in order to get accurate estimations.
Right. Thank you for your answer. I think as you just explained, so I asked something that is very much related to that, and which is that there are a lot of assumptions that you've taken when setting up your experiments, right? And that's always one of the challenges of having these ensemble representations of the soil matrix. So how do you see some of these limitations or assumptions influencing, like, for example, if you're modeling the flow of water in a 1D dimension, what are some of the limitations that you foresee if you want it, if you transfer these learnings to, let's say, another optimizer?
You mean so I think there are two questions here. Like first, you wonder the limitation when we are assuming a one-dimensional dimensional flow. Yeah, so like one-dimensional flow assumption, it would fail when we are using this drip irrigation and when we considering the soil heterogeneity because water flows horizontally in different directions, not just vertically. So that is the limitation. So, and this is one of the motivation that I carry out this study, like to like not assuming the vertical flow, not assuming vertical flow, that there is a significant amount of horizontal flow, and we carry out the study in a representative setting of drip irrigation. And the other problem is the other question that you ask is about the.
I'll repeat that. So I think that the other part of my question was how these limitations, like for example, if you're saying that the flux is just moving in this direction, how do you think that influence the results or the conclusions of the study?
Oh, yeah. So I think using the one-dimensional flow assumption is not a good one if we are doing a drip irrigation. I think that would give us not accurate result because that assume that flows uniformly in a horizontal direction, and we cannot study the non-uniform flow pattern. I think this is a quite large uncertainty here, and that 1D flow assumption can be used if we are doing a spray irrigation, but we cannot apply it to a drip irrigation. And also the limitation in the field study is we cannot apply the soil heterogeneity of different that soil varies in space and vertically and horizontally. So these are the limitation of the 1D assumption that I carry out the study in a 1D setting in my first paper like 1.5 years ago, but my recent paper just addressed this challenge, like not relying on this assumption.
Thank you very much for your answer. So we have some questions from the participants as well. And there's one question which says that, are there any numerical methods, or can we measure them by some telemetry to find the evapotranspiration rather than estimating it for a lake? Okay, so it's that if it was a lake and we wanted to find evapotranspiration, so are there any alternative numerical methods or any remote sensing based methods for that?
Yeah, so there are some forward models to estimate the evapotranspiration rate, but it is none of them is a direct measurement. Evapotranspiration rate, like we cannot say it is a accurate number how much water is uptake. That is impossible just to give you the correct number. We have to rely on the information like soil moisture, like temperature, and other observations from the soil surface or the soil moisture. So there is not a direct measurement of the evapotranspiration. We have to rely on these data simulation techniques.
That is true. So evapotranspiration is known for being a very difficult variable to estimate.
Yeah.
Are there any other questions from the listeners?
Yeah, Julia, can I ask a question here?
Please.
Sure.
First of all, thank you very much for a very brilliant work and presentation, and really learned a lot from that. And I really am looking forward to seeing some field results, whether you do it yourself or some other person tries to validate your results. That would be immensely interesting. So one of the things that I wanted to ask was about the Richard equation itself. I mean, it is very well known that there are very strong nonlinearities in that sink term that you use.
Yeah.
how much of that is a hindrance in the data assimilation method? Because are you using kind of a simplified model? Are you using the full blown Richards equation in your numerical implementation?
Oh, this is a great question. I did use the full Richards equation, and this is highly nonlinear, and in the sync term is nonlinear too. And the ensemble common filter is applied in nonlinear system, but we have to check because we assume the Gaussian distribution of the parameters, the potential transpiration, and the maximum evaporation rate, and we need to check if we solve the Richards equation and get soil moisture, then we can plot the distribution of this sync term and check if they are Gaussian or not. So, and I did check it, and we can get a good pretty close to Gaussian distribution. So I think this assumption of the Gaussian distribution in the sync term would hold.
Yeah, great. And what about the parameters themselves? Are you assuming any uncertainty in, because I mean, it's a very spatially distributed parameter field. So again, I'm thinking of a field level verification. So of course, what you are assuming in the numerical experiments, they can be known to perfection because you yourself are assuming that. But what about any assumptions on how much uncertainty is there in the parameters themselves?
Oh, yeah. So this is also a great question. So I think the question is about would these Tmax and Emax, they are also spatial dependent? Yeah. So here we do not treat them as a spatial dependent variable because we treat the spatial variability in the root distribution. And then the sync term is spatial dependent. Yeah, I think these are the models that people commonly used for like 2D transpiration and evaporation.
Right.
Yeah.
And then finally, the sensor placement itself, are you assuming some kind of a regular grid, or again, the placement is, I mean, have you experimented with various sensor configurations, like maybe randomly placing the sensors in the 2D field, or using some kind of a grid? Is there any implication on the choice of this sensor placement?
Oh yeah, so my current implementation, I use this very ordered placing of sensors, but it could use like different configurations. We can choose where should we place the sensor. Should it close to the root, or between two plants, or close the surface? So with this two methodologies, we can investigate where to place the sensor, but I haven't done it yet.
Yeah. And just my final comment would be that if you are going to look into that, perhaps the practical question could be, what would be the minimum number of sensors that you need to place there? Because putting in the sensors requires cost, and that requires a lot of effort as well. So if you can somehow find the optimal minimum number and the placement of these sensors, that would also be a great result. Yeah.
Oh yeah, that's right. So we did carry out study the effects of number of sensors in a previous work last year. But it's for the one-dimensional study, and we only used the 4 sensors to get good results. And the conclusion from that paper is we need a sensor closer to the surface. Yeah.
Sure.
Yeah, thank you.
Thank you.
Okay, so if I may, so Vayu, thank you very much. I thoroughly enjoyed your presentation, and it's wonderful work. So thank you for that. So I would like to ask about the assumption of the irrigation system. So what exactly in your formulation does drip irrigation thing, what restricts the scope of it. So if it were, for instance, like sprinkler or flood irrigation, I mean, the Richards equation and that would be the same, but what would change then?
Oh, yeah. So I think I would refer to this slide. Like we can see the top boundary condition where the water flux equal to the water flux from the dripper, like P is the flow rate from the dripper, and the LD is the characteristic length scale of the dripper, and these are the dx is the location of the dripper. So we consider how much water is provided from the dripper, and also the evaporation is a water loss from the surface. So we should deduct that amount to get the total amount of water into the soil domain. So the change is on the top boundary condition. This is for the drip irrigation setup, and we have like a sprinkler or spray irrigation setup. So we replace this. So we do not have that spatial variability, because like for the rain, we have the same amount of water flux everywhere. Yeah.
Yeah. So for the flood irrigation, it would be a simpler term than this.
Yeah, that's simpler term. So that in that one, we carried out a 1D simulation only, because the flow, we assume the flow is uniform, like everywhere. If it's a rain.
Okay. And these terms of Tmax and Emax, the maximum transpiration and evaporation. So this assumption of both of them being independent, how restrictive is this? I mean, is there any correlation between them in practice, or is the assumption safe enough?
I think this assumption that they are independent Gaussian variables. That's how I treated them, and I think they are widely used by people in the literature in modeling this transpiration and evaporation.
Okay.
Yeah, I haven't seen any work discussing they are like correlated, whatever.
Yeah, and you mentioned the characteristics of the soil that you need to input into the simulation. How extensive are those? What do you need besides the soil texture? So if you have the soil texture, you have empirical relations that can derive all the parameters for you. Do you think if you were doing a field study, would that be enough, or is there something else that you would need for that?
Yeah, I think only thing I need is the saturated hydraulic connectivity in the soil.
All right. So if you have the texture, then this could be derived from that.
Yeah, from the texture, we can get we can estimate the hydraulic connectivity.
Okay, so that were all my questions. Thank you for answering them.
Yeah, thank you for your questions. They're great questions.
Javeria, can I just ask one more? It just occurred to me. So you were concerned about these horizontal flows, but in many irrigation schemes, you may be aware that people actually use these raised beds. So the irrigation is on the sides, and there are these bed-like soil structures in which actually the moisture comes from the sides. So it is a horizontal flow by design. Have you considered those kind of soil topographies in your work yet, or are you aware of that?
Well, yeah, so for this kind of irrigation system, I haven't studied them yet. I think then, but my numerical code could apply this irrigation system to modify like the upper boundary condition and to study this behavior, I think.
Yeah, that seems like a very interesting extension, because again, by design, the irrigation system is supposed to work this way, that the roots, they actually take in the moisture from the sides and not coming from up. So that will be very, very interesting to see what kind of simulations does.
They plug in this this watering system inside the soil, right? And then I think then we should fix the left and the right boundary. There is no longer a non-flux boundary condition. There would be water inside, and then we do not have this water flow from the dripper from the top surface. Yeah, that would be very interesting.
I think we will stop here and thank our speaker again for the wonderful presentation and also for answering our plethora of questions. Thank you very much, Dr. Lee. We'll stop the recording here and formally end the seminar, but if you can stay just for a few more minutes, Dr. Lee, we would appreciate that.